and welcome back to Evening Rust because it's evening somewhere, so we're just going to do it whenever time I have time. I haven't been around for a week, and I've been busy doing other weird stuff, been sick a few times, but now I'm back and we're ready to keep going with the tic-tac-toe. I have a few ideas there, and I worked through something called fractal AI, and we'll get back to that. Let's start the show as we always do. Let's go to one of these. Clash of Code, and I'm never going to remember the name. See how we do today. Last time we did really well. I haven't done Rust in like 2 weeks, so maybe I don't remember enough. Maybe we're going to do poorly, maybe we'll do well. After this, we'll get back into tic-tac-toe. And as I said, I looked at something called fractal AI, and fractal AI is, as far as I can tell from looking at the code, it's actually kind of a variant of the Monte Carlo search tree. It reduces the number of iterations. It has a kind of critical flaw to it, which is going to hurt us, and it comes down to the scoring. Without a scoring algorithm, we can't really use it. And by scoring algorithm, I mean, given the state of the board, predict who the winner is going to be, essentially. I mean, what's the value of the board, who has the more chance of winning at a particular state of the board. Without that, there's not a lot we can actually do with fractal AI. So we're going to have to look at some things, but today what I want to do is, before that, I'm going to refactor a little bit more, because what we have is we have opening moves, and we're going to have to refactor out the actual scoring part I just talked about to provide different scoring opportunities and back end. So we're going to make our strategy a bit more structured to be able to apply at a high level to test more than just the parameters of the Monte Carlo search. Let's try actually fundamentally different things. And that's what I'm going to do today, as soon as I've done this Clash of the Code repo. And nobody I recognize so far in the Flash of Code. Say hi here, and we're going to see what happens. If we can't get the tic-tac-toe further, now we're in debug mode in the code, but there must be a way that we can get further without that. Obviously, if we had release mode, we would definitely go up some of the ranks, but I'm not convinced we will actually get to the top even with release mode. It's actually, since the other guys will just be compiled in release mode as well, there must be a strategy we're missing here. And the top guys, we'll take a look at where our rank is when we get back to that. And let's hope something not stressful here. Still waiting. More people's better for us, as always. Our ranks are fairly high. If you see, all my windows have been open here. I've been doing GL stuff, SDL, through SDL all morning with Leaf, and it's been weird. There's a lot of weird stuff in GL, a lot of stuff I have to take advantage of or take care of that wasn't expected. The biggest one of the pointers, that's kind of a headache, trying to create a window, but I'm trying to get to the point where I can just create something on the screen. And I think we're far enough, then pretty close in the Leaf, that I can start maybe next week or the week after, start doing the live broadcast of programming a game. We're going to start with the Tron-like Snakes game. We're just going to start programming it in Leaf and go through from the beginning how we start up, how we set up, and how we program the game. It's like the one we played here with an AI, but we'll actually program the game. And we get to do it in Leaf, and you can also see how we do basic game programming as well, how the state works. And it's going to be a bit of a rough ride, though, because there's lots of bit missings. So usually these start up a bit faster. It's okay. Running out of stuff to say until we get back to the code. So hope there's somebody around at this time of the day. I know this is not a usual time for me. It's the only time I had this week, though. Let's say it's evening somewhere, so let's go. Let's see what we get. Not golf. Not golf. Not golf. Not golf. Just do it fast. Reverse of it. Oh god, I have no idea how to do that. Actually, fine. Let's find out. Let's do W equals S. Let's split white space. I think that works for W. Let's just do R in r.iter.rev. Why is it expanding? I mean, this is stupid. Print R. Does this work? It must be an iterator already. We need to have a space after it. Well, why did that do nothing? Well, we're doing poorly. Found hello world. If I print a space, why does it completely do something different? Alright, because the last one there is a space. Ah, crap. We're going to have to do a space. I know there's probably a join here. First equals true. Not first. First equals false. Wow, we're fell behind it. This is a bit tough. There is a join operator, and I just don't know how to use it. That looks good enough. So that wasn't so good. There is a join operator in Rust, but we don't have a lot of chance in these time things to actually look it up. And so these guys know their language fairly well. PHP, Python. Let's see how it's done in Python. Yeah, there's a reverse. And so he said there must be a join, and that would be the quickest way. And I didn't know what the join is, so it cost me a bit of time there to do that. But that's okay. We just like playing with and see random stuff. Our ranking goes up and down here because of it. Whoops. Oh, so next month there's a contest. Which April 20th. I'll have to see if I can do that. I might not actually be around for that. Let's see what we have. But let's check my score. And so we slowly drip down here, and we have a lot from the contest. Generally, it's the Clash of Code where we keep dropping down, because if you don't play, you fall down. And it's because we're so high up in the ratings here. At rank 241 globally, any day we don't play, we actually drop in the ranks. So that's why we play them. But if we don't do well, I don't know if it keeps us up in the ranks or not. But let's go off to tic-tac-toe. Tic-tac-toe. Where are we? There is no... We're dropped down to 77th, so we're not doing so well. And let's check out the leaderboard first of all. This is getting to a point, these guys have optimized to the point that I don't think just running in release mode is going to help us get very high in this list, maybe somewhere around here. But the gap here is pretty big, so we're going to have to actually look for things that aren't just going through a tree. Let's load up the external editor. And Tom, you're welcome. Are you up there? Where are you on the leaderboard? Did you make it to the gold? Or are you in the bronze? Or where'd you make it to? Let's see where Tom is. Is Tom up here? There he is. 101. Not far behind us. Using Rust as well. That's great. Just heuristics you're using. Wow. This is what I'm trying to do now, is that we made it to our position now using no heuristics, using just search tree. And so I'm actually going to go to the point now is that I'm going to split up my strategy to use both heuristics and search tree, and maybe use a combination of it and see if we can get higher, because search tree we just don't have enough iterations, and I'm going to restructure now to get there. You're not very far behind us at 101 there. But I'm guessing most of the people in gold are using some sort of search tree combined with heuristics, because search tree itself, again, if we weren't in release mode, we'd get somewhat higher, but then everybody else might get higher, so it's hard to say. But I'm glad you found it interesting. I'm glad you made it to gold. And now I'm going to work from here. So where we are, 77, and let's take a look at code. I don't remember where my code is. I did a tiny bit offline. I made this little strat factory things. I don't think we made these last time. So my strategy thing here, strat factory, now takes two factory objects to create player 0 and player 1. And it takes the name of a player. And so the idea here was that right now when we run this, let's see if it's still running. Clear and cargo build and target. Play, no, debug, play. This does a whole bunch of iterations. This code does a whole bunch of iterations to tell you who has the advantage to win based on the two codes. And this is our local iteration. So right now we're evaluating two strategies, a Monte Carlo with an initial move and one without an initial move. And we're trying to see if that actually has a chance of winning, what it does. And so far it's been proving that the guy with the initial move playing to the top left actually has a slight advantage, but that might be unfair. And it's the first thing I want to check is that, is it just because he's a first player or because he's making that first move? And so this is what I actually want to test. And so for that I made the two strat factories and had a bit of difficulty in Rust, but now I have these closures. And I think a little unfortunate in Rust is that you can't use closures as functions, and that's kind of annoying. There's always this casting involved. You can cast them, but you can't pass this directly to a function that takes a strat factory. So it's a little bit weird. I am not entirely clear on that. Okay, but now what we're going to do is inside the score 1 here. Okay, so you can see that player 1 has a slightly improved chance. Out of 1,000 games, it has a score of 52, which is basically wins minus losses. So by having that starting position, it has a better chance of winning. But I'm wondering if that's also not just because it's the first position. So we have to modify this score 1 to take a random first player and find out what happens. Let's do a random. How do we do a random again? Let first player equal, what do we have for random? We can just probably do this. RNG get, or, oh, I don't remember how you get a Boolean. Well, I can just do that next U32. Mod 2? Mod 2. And strat 0. Oh, just how does this work? Trying to think of how to set this up. It's supposed to be fairly simple. We have to pass the two strategies, but we need a little array of strategies instead. And we just do this equals 0, swap player. Then we can work through, and then let's say let mut-strats equal. I think we create an array of them. Swap player. I don't know how well this works. Swap player, then P11 else P00. This is supposed to be 0. I'm trying to think of how this works here. 0. So we're trying to swap the strategies. Otherwise, it's player 0, 1, player 1, 1. This should create an array of two strategies. Play random steps doesn't matter here, just opening the board. And now we have add midpoint strategy. This is a bit weird. Those are boxes. So what do we have is strat 0. It's the first player. Strats 1 is the second player. It starts with player 0. And so tie is still 0. Now we have to do this and swap player. And not swap player. Okay. So it's going to swap the scores as well. I hope that makes some sort of sense to that. Let's reduce the iterations for a second. Thread RNG. Let's look at the state. Ran thread RNG. Should be there. Thread RNG. Cannot find, what am I actually calling it? Thread RNG, thread RNG. It's not yet, it's just this. Okay, mutable second world. God damn it. Of course, this This is one of the borrowing errors that angers me in Rust, is that there's a lot of times where you can't use an array, which logically you can, because then this connects them together. Well, we're actually literally going to have to do something stupid like this now. Strat 0 equals... Now this thing works. This is actually, I find, is an actual weak point in Rust. In my mind, logically, an array of 2 length is cleaner than 2 independent variables. Now with 2 it's not a big deal, but if you had 3 of them, and there should be absolutely no safety issue with taking an index from each of those, and I think it's an actual error in Rust at this point in the borrow checker that it actually does this. I know it's technically not an error, but it kind of annoys me that it does that. So now we have a different score here when we swap the position. We're not playing as many games, so I just want to see that it works. That's weird. It's hard to tell if they have a bad win. Let's put up to 1,000. Let's run it once. And that would be then basically that our heuristic of starting at the top left is not very efficient. We're trying to figure out whether that actually makes sense. Whether it does or does not, I'm actually going to restructure the code so that we can plug in these heuristics now and see how it actually works. So a strat is going to be comprised of a couple of extra moves. A strat's going to be comprised of the Monte Carlo search and of a heuristic, and the heuristic one is going to say, should I make a move? And if it doesn't, then it falls back to the other approach. So you're going to have a fallback strategy and seeing how that works. So 1,000 takes a while. We won't run lots. Now hopefully my logic is correct here. But I'm just randomizing who strat 0 and who strat 1 is, and the players are swapped. I swap the scores out. Oilers just all, I was actually thinking about that, yeah. You're actually quite right. Not a XOR, but Boolean compare. So if it's player 0, 1, and the players are not swapped, then it's 1. If it's player false, I think that should be correct. So the XORs, yeah, the XORs, what I'm doing, equals equals is essentially I don't think one equals. I need to think about that logically. Well, let's try not to be clever about it. Let's just try to do it the quick way. Let's do it the correct way. If swap player else. Let's just duplicate it and then worry about the actual logic, just so we're not fighting about it too much. So if the players are not swapped, we return the old one. If player equals 0 equals 1. And this can actually be combined to a XOR and equals. I don't want to tense it right now. Like that. Now obviously we could group that together. I just want to get it correct first, and this is not going to make a big difference in the speed of the code. And then logically you can at least see what's happening. If we are swapping the player, it's a player 1 1s, we return 1, otherwise -1. Let's just, oops, let's just kill that thing down here. Yeah, that's correct, because I'm thinking the old way I had it and now swap player would be stupid because it would only ever be the one result. Yeah. Alright, so this should be better. Thanks, Oiler. And then we got some results here. We came in 5th, obviously. So the next competition on April 20th, I don't know. I don't know if I'm going to be around. I mean, I could be around part of it, but if I'm gone one whole weekend of that, that cuts into the time significantly in what I can do, and we come in quite low. But if I do have time, I'll enter it and just see what happens and play for the best. And I won't, because one of that week there, the last week in April, I'm not around and I don't have the right computer, so I definitely can't stream, and I don't even have the right computer to do the coding on. I'd have to set up everything again. But we can do like a bullet thing. Try one day, see if we get it. Okay. All right, so if we're correct now, this is like fairly dead equal. The starting position in 0-0 gains us absolutely nothing. If we're correct, let's run it again just because I'm not convinced of that. And this was a starting one saying if we are the first player, start in position 0-0, and it looks to get us absolutely nothing. In position 0-0, these are linear positions. This is the first big grid 0, and then the small grid 0 in it. These are from numbers 1 to 9. This isn't position 0, 0 on the board, although it happens to be the same thing in this case. I'm just verifying this again. This position buys us nothing, and then we just remove it. And then we'll start looking at some sort of heuristical approach. And the long-term approach here is it comes down to the scoring function. A lot has to do with the scoring function. And we don't have a good idea for the scoring function. Now, I had another option of how we can improve the Monte Carlos. Right now, it takes a very slow approach of like actually playing the game from whatever position you are, plays the game to the end. There is another option here. And okay, let's look at this. It's not like dominantly winning, so it may or may not win, and 1,000 probably doesn't look like it's enough to figure out whether starting this position wins. The randomness wins often enough. The scores just aren't high enough. I wouldn't worry about that very much. Okay. So now we're going to do a different strategy, though. We have the strategy. These are in tests. We don't need that right now. Now, what did I do for the play? I created a strategy called Monte Carlo Predict. And Monte Carlo Predict has get turn. It has this if first self first move is sum. And there's nothing set. This is the part I want to take out of here. I want to have a combined strategy instead, saying, look, we need a heuristic here. So what we can do is we're going to create another strategy now. What was strat local again? Oh yeah, that was a gets best small move. Strat local was the one that... Yeah. Now let's put these all down where they belong. Again, normalized split is all often individual small files, but again, it's something I actually don't like about Rust. Is every time you create a new file, you have to update the lib file. It's kind of like a project file, but it just can't figure out. You can't lump files together. You can't just simply move files to other ones. You actually have to worry about imports and everything then. And let's do strat. I don't know what we call this. Strat phased. It's going to need the player as well. Use size. And it's going to have two strategies. It's going to have the heuristic one. Why on earth is heuristic showing up? Heuristic, and this has to be a box strategy. I think we own this thing. And then it's going to have the fallback box strategy. Now what the strat phase is going to do is it's going to ask this one here, the box strategy, and actually it's going to have to be, crap, a different strategy. It's going to have to be an optional strategy, which is basically the same thing. I'm going to say if get turn. It's going to return an option. The reason it's returning an option is this one might actually say, I don't have anything to do. Don't do this. Don't get the turn. It may say, I can't make a good decision. And that lets us have two options here, a boxed op strategy. So the strat phase itself doesn't have to decide whether it makes a decision. It asks the first strategy, do you have something in mind? And if the first one goes, nope, then it falls back to this one. Okay, so implement strategy for strat phased. Just copy this up here. And what we can do now is simply do match self dot heuristic dot if get turn state comma force. Force is again the force move you have to make if you're on the big board. Some R, then we return R. I don't know why it's highlighting like an idiot here. I just return R. Everything else we're going to return self.fallback state comma force. So our strategy here is very simple. The phase strategy basically, and either the heuristic returns a value or it doesn't. If it doesn't, it goes to the fallback, and if we do have a heuristic one, then we use the fallback. Fairly straightforward. Strat phase, so we have to implement a new operator, and yeah, we just called it new. Function new. It takes a player of usize and it returns a strat phased. Does it return strat or box? Can't remember what we returned. Box, I think. No, just self. Self, yeah, that makes sense. We'll let something else box it up. Oh, this actually has to take two other strategies, of course. And the heuristic, it's a box up strategy. I don't think these are boxed here. This was only for the main thing. We don't need these to be boxed. It's going to have to own these strategies anyways. So let's just take ownership. Again, the default in Rust is to move it. So whenever you see something like this, it's moving it. And fall back. Strat phased, and we're going to do player heuristic and fallback. And this will create the phase bit, the heuristic bit, the optional strategy. That'll combine them together. Now the one thing we wanted to do is we wanted to add the strategy pub struct upstrat opening move. A very, very basic one. And if you're asking yourself, why am I repeating player in every single one of them? It's because there's no way to actually do abstract classes in Rust or reuse bits of other strategies. So if we have a bit that has to be reused, you basically have no choice but to actually just duplicate it everywhere. First move. Now this one has, it's not an option, the first move, it's just the first move because it has no choice about that. And I really want to put these in other files, and I know it makes it complicated, because then every time, the moment you put it in another file, you have to stick it in lib, and then every place it wants to use it has to import that second file. So it's actually effort to move things around. It reduces the refactoring. I mean, it reduces the rate at which I refactor for having that overhead, and I'm not a big fan of that. I mean, I think there's something wrong here. I can't pinpoint what it is. Imports and stuff makes sense. But to me, it's wrong when refactoring to simplify your code increases the amount of code without gaining anything. It seems like a little bit odd. So I'm going to stick these all in one file for now because I don't have an easy way to split these up. It wouldn't be so bad if I just had to put them in one face in the lib file, but that's not enough. You have to put in every single place that wants to use this strategy then. It's not like in C++ and refactor, you add them to the one header file and then it includes it in all the other ones. You don't have that option here. Implement upstrat strat opening move. Hub function new. Okay, so Tom's saying we could actually put them all in a directory and import them all. The directory, use strats. But then the builder doesn't work. We're going to have to look at that, because if it's something that works, we can submit a patch to ep24's builder that would actually scan that directory and just include all of them. That would be an option. Well, let me look at that offline, because I'd really like to actually get that working. If you do get it offline, that'd be great, but if we can get ep24's builder to support that as well, that'd be also great. We can fork it and try to get that working, because it is kind of a pain to do that over and over and over, and we'd prefer not to. Okay, first move. Use size, use size. Now we keep putting use size here everywhere. We never did create an alias for the move. We're not sure if it's good or not. It's a very simple structure, and I just haven't created an alias for it. I don't know if we should or not. Implement op strategy. Now, what do we call it? If get turn. Where's this first move stuff? We're going to kill this first move stuff first of all. If first move. No first move on Monte Carlo anymore. There it is. Take that one. Oops, and that's this. So if nothing's set, then we return some self.first move. And as we return none, we don't have a move. So that's our optional strategy for first move. Now this stuff here gets a little bit different now. Box new strategy Monte. So this now becomes upstrat. No, this becomes, what do I call it? Strat phased. Zero on new. And the first bit is a Monte Carlo one. No, the first bit is heuristic. So the fallback is this one strat Monte Carlo new player sum. Nope, sum. Take that out. Up strat first move. New player, and we said 0,0 is the first move we wanted. Okay, if we did this correct, that should give us the same thing. Did you mean strat phased? Probably 266. Did you mean, ooh, a plater? Who is a plater? Uh-oh. What's wrong here? 262, 262. Oh no, we're gonna have to use boxes here as well. That's right, because you can't have pointers to traits, so we're gonna box it up. Unfortunately, we have to box it up. But here, because it moves it in, we should be able to do it here. I understand why it's using boxes, and I'm getting used to using them. Something doesn't quite feel right with them, though. Is this a colon instead? Oh yeah, entry's gonna have to do it too. Monte Carlo predict. We'll just get rid of the first move for now so it doesn't use it. It wasn't buying us anything anyways. What do we have? Oh, you can't do that either. Well, that's a bit weird. Why is my fan running so much? OBS is barely even doing anything. The fan on my computer is going crazy for some reason. It's got a low temperature, but, you know, that's because the fan's going crazy. And everything's recording here. Low things. Weird. I hope you can't hear the fan. I hope it's not interfering with it. I actually don't know what's making it go crazy. Because it's not even spinning that fast. Whatever. Hopefully the sound isn't a problem. Okay. So why... Well, this is kind of annoying. I was not expecting this. Why did these need to have... Oh, yeah, because they're strategies. This is... I thought they didn't have to, though. It's because I need to keep their lifetime? I don't know about this. Well, how do I create boxes here? Box new. Trait up strategy. Huh? Yeah, okay, so I already have boxes, so I don't need to do this. Go back to this. If you're used to a higher level language, the box is just going to kind of be annoying, and there's a lot of boxes everywhere. I just compare them to kind of like creating a shared pointer and managed pointer in C++. Field, not a method. Yeah. Oh, come on. Come on. Give me a break. Well, that should have been used. 302. Well, this has to be forced out is none just to satisfy that it's used, but just for correctness. Play 127, 127. Upstrat first move. Did I call it something else? Upstrat opening move. Okay, fine. I don't know why I called it that. Unnecessary parens. I don't like that part of the linter. I'd actually prefer to turn that one off. But we're trying to write code that's correct with their linter. Alright, that's open. I'll just ignore it. It's just... I don't care. I'm going to take the warning for now and play 130. This no longer takes that. Okay, so what we've done is we split this up so we can do different sets of the strategy. We take the first move completely out. It buys us nothing on its own. And we might be able to have a different way to evaluate strategies now, and a different way to do the fallback. With the Monte Carlo one, we can replace Monte Carlo entirely. I have the other idea in Monte Carlo. Well, instead of play to end, that's one of the things I want to say. We could check how play to end works. Because play to end right now actually plays to the end. There's another option of simply taking every free cell and sticking a random value in it. A lot of these boards aren't valid, but that is probably faster, and it might still represent valid, like roughly, because modules are sampling at random, it may still represent a good indication of whether that board can win or not. That is, if you have a few empty spaces, if you just build them in with random values, like alternating between x and 0, x and o, x and o, x and o, x and o, if you just alternate between all of them, assuming they can play anywhere, and then evaluate the score right at the end of that, will that with the Monte Carlo actually give a fair score overall? Will it give you some indication of what should be done? Okay, I'm not sure if that's helpful, but okay. Phase strategy, we have this, and this just opens up our code a bit more. It doesn't buy us anything directly yet. So now I'm trying to think of what can we do before that playing. So I say one of the big things we have is this predict here. Predict state. And predict state is one thing I'm going to pull offline as well. I'm going to put this into strategy. I'm going to let the strategy say, hey, look, this is how you predict the state, and let the state predict that. And so wherever we call predict state, you're going to have to tell it what the predictor is. Play to end, where's that called? And we're going to have to pass this all the way down, which is a real pain now. When you have a function like this, predict state, you have to structure the code around the idea that how can you actually predict the state? And this is where it's going to be a pain with Rust, because I tried to do that before with factories, and setting up factories functions are kind of annoying. You can do this. And so basically we're going to do a predict state, and I'm not sure if we should do a function or a trait. This is the key here, is that, well, the predictor, is it a mutable thing or is it an immutable thing? Does the predictor actually need to know, does it modify the state? Probably not. The predictor has to be static, so we can probably make a predictor function. And the predictor function is going to have to be, well, how does it predict the state? And that'll move this predict state out of line. We can call it out of line. And it takes a state. Predict state takes a state. And we only need it for the big board, or actually for the board state. So predictor, it has to take a predictor that takes the state. So how do we declare these things again? Type strat factory. We're going to have one of these. We're going to say strat predict result. This is a function that takes the state of board state and gives a game result back. So this function, now we have to anchor it, is in the strategy somehow, and this is where it gets really annoying, that each strategy it wants to use, it's going to have to carry it on its own. So who does play to end? And maybe the whole play to end itself should be pluggable. We can make that after. Play to end is only called in one place, and that's in get best move score, get best move score. It's called in one place, which is only in Monte Carlo, which is good. So that means Monte Carlo needs something to predict the state. And so this needs this predict, and it needs predict. What do we call it again? Predict result. So Monte Carlo needs something that predicts the result of this stuff. And then we can start messing with that. Predict. Okay, and then we have get best move score. And now we're going to do this as self on this. Self.get best move score, so we can use this. And this is calling play to end. Play to end. Who calls play to end? It's really strange that just Monte Carlo does that. And we're just going to give it a predictor here as well. Predict. Predict result. And so we're going to do predict state. Let's get rid of this to do because we're going to play with that a bit. And so play to end. Play to end is going to take self.predict. Okay, now how do we declare static functions? Well, these are all static unless it takes self. This question, can I just use this as a static function? Well, let's find out. Where's our Monte Carlo here? Let's see if it accepts this or gets mad at us. Put this on a new line. Oops. Let's take out that play, I guess. 101. Oh yeah, we need a self here. And self. And I don't know how to get this. I want Cargo to be able to build just one program, not all of them. But I guess entry is part of it, so I have no choice there. Board state predict. Predict state. Okay, so apparently this works. Okay, so apparently you can just take the function as a static and get its address, and that is kind of nice. That's a nice thing that there's nothing special about these functions. You just want to take self, and that lets us move predict state to a totally other file, which we're going to do once this works. We're going to create a new other file and call it predict. And this is for the board state. And this helps keep these classes clean, as they're just basically like this doesn't have anything in it, except now we have these functions here. I'm going to make a file for this. We're going to say predict.rs. Now, what am I doing? Okay, and this has to be like strategy. It has to use state star. Use state star. And this takes a... Now self just changes though. So now we have a... I don't know if we can call it self. Let's call it state. And this is an and board state. And all the self dots become state dot. Okay, and a small board predict state we also need, so we're going to find predict state in there as well. We tried that inline always to try and get speed improvements. It really didn't seem to do anything for us. We can leave it there. I don't know if it's hurting anything, but state and small board. Oh no, it's going to get mad at us for the overloads. Again, I actually prefer overloads. I don't like not having overloads, but it's not an option unless you do a trait. State that small I. Okay, however we call that, it's just going to become We're just going to leave it called predict state for now. We'll just say predict state. This would be predict. We'll just leave that as a default name. Use predict star. Did I mark everything public in here? I did, and play is going to be the same way. Use tic-tac-toe predict star. And what this does is it separates out the predict function from the actual state. So the state knows nothing about prediction anymore. The state becomes more bare bones. It doesn't want to do heuristics. It's just storing the states. Entry, where is that? Okay, we need a lib file. So I mean about the lib file, hub mod predict. Don't need to run that. And undeclared module predict and entry. Why? What's its problem now? Let's go look at predict first and figure that out. Predict state small dot I. Yeah, that one makes sense. Let's just hope that goes away. It won't, though. Undeclared typer module predict. Predict. It's in lib as predict. And entry is use predict. Oh, because we don't need the predict there now. That's right. We just do this. Yeah, same with over there. We just say predict straight because we've imported all of that. Probably didn't need to import it, but we did. And this pub state file, this is not actually public. And see if it still works. We'll let it run. And so we separate out the predictors. So now we can actually play with different predictors. And the idea here is that we might want to play with how it predicts the states, whether it wins or loses. Now, when I looked at the fractal AI, it's absolutely essential that this predict state can work because the fractal AI approach, and again, the name is really, it says a lot more than this. The fractal AI from the document I read is really just it's a slightly verified Monte Carlo that instead of doing a full walk, it opens up like say 20 walkers in parallel and does one step on each of them. And at every step it predicts the state of each of them. And if it's finding winners over losers, it starts moving some of the walkers into the winning one or into the losing one if you're trying to do the minimum. And this just helps you focus on the winning areas. But if you don't have a good predict state function, if you don't have a good scoring function, that's absolutely useless, that approach. The approach was mainly made for games where you have clear scoring and graphic input, where you had like old Atari games where you just had scores that literally go up and you track the scores, and it's very simple to track that then. Or if you have distance to end or a time, tic-tac-toe, it's not very clear, given a board state, who the likely winner is. So we can actually start testing this now. So let's actually do this. Let's do pub funct predict, no predict. Oh yeah, predict current. Let's do predict current. And we want to see what happens here. And this is just to verify that the predict state is actually having an impact. Yeah, before we start to optimize, let's verify it has an impact. And let's just return state dot get state. We don't care. Whatever the current state is of the board, we're just going to say that's the predict current. And we already said opening move wasn't helpful. So I'm just going to comment this out for now and simplify. We'll just predict current. So the first player is essentially not doing any prediction. The first player is just saying whatever the board is the board is. And we're going to see how much this affects our scoring. Ideally, what we're thinking is that this should really hurt player 0. If this doesn't hurt player 0, it indicates that maybe we have something else more fundamentally wrong. Because if player 1 doesn't overwhelmingly win here, then we have something else horribly wrong. Because player 0 is effectively making a random move, it doesn't know what the Monte Carlo result is. It just has no idea. It's Monte Carlo result, it just has no idea what the result's going to be. And so it's just going to be guessing at random. So what we're hoping to see here, what we're predicting, is that player 1 should overwhelmingly win because its prediction algorithm is okay. Now, you're kind of secretly hoping that it doesn't, because that's very clear. It's like, oh, then we screwed up the scoring so badly that that's why we're not doing so well in the game. Now, there's also an ordering thing that technically you could say, well, maybe your predict function is a thing that should actually invoke Monte Carlo and not the strategy, right? There's kind of this looping here, because then you can make another strategy called get best move that just tests all of its moves. And for each of them, okay, this is really bad. This is really bad. And this is just... yeah, I lost what I was saying, but this is actually, like, say, I'm just focused on this. But this confirms why playing with the heuristic wasn't actually doing us any better. I mean, the predict current will still work once you get to a far enough depth. And that was this value here, the depth of the board, how far it goes. And since most games are finished in 50, and this is just awful, the first player actually, we're just doing randomness. But if I put the depth down to 10, hopefully it makes a bigger difference. We're going to have to start hunting through what the issue here is. Weird. Weird, 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 weird. Trying to think of what the issue could be. Is our predicting state so bad that it doesn't help? It could be. We can make a predict random to find out. Well, we can actually make a predict that inverses the prediction. And that would force it to do bad, so it chooses failing ones instead. Except it only goes in predict. It only works when we're actually predicting it, so that won't help very much. Alright, this 1,000 iterations, it's really slow, and because it's time-based, running a release won't help, it'll just improve the quality. It'll still take just as long. That's sad. The lower the depth is, it's really sad. The lower the depth is, the better predict current gets, which would indicate we're better off not predicting anything. Alright, give me 1 second. I'm going to take a short break and run off. I'll be back in just a couple of minutes, and we can keep thinking about it. If you have any clever ideas of what the problem is, let me know in the meantime, but I'll be right back. Alright, I'm back, and I see your idea, I guess. In terms of prediction, yeah, that's basically it. I mean, our predictor is crap, or we're not using it correctly, which is kind of the reason why I wanted to separate it off. I wanted to figure out, can we improve the predictor? So predictor of current works even better. Let's create a new predictor, one that's even stupider. Let's do predict opposite. We're just trying to prove that our algorithm is actually using this. And the predict opposite is just going to make a horrible, horrible prediction of just making things even worse. Match state.get state. And closed is going to return, yeah, game result closed, game result open. So this is just going to do an awful, awful, awful prediction. And we really want to see that ones using an awful prediction should actually fail. And we just have to verify that the code's actually working. And because if this doesn't make an even bigger difference, then something else is totally screwed up. Win x. Win x plus 1 mod 2. Those are the only results. We have close win. So we have a predict opposite. Now we predict current, and predict current is winning, so let's do predict opposite instead. Opposite. Put these back down to 20 or 30, wherever it was. That should be good enough. Now, player 0 with predict opposite, and should have a horrible, 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 horrible score, because he's actually predicting the opposite state in the initial parts of the game, doing something random. But of course, if predict state's no good, well, we're assuming predict state isn't total garbage. But maybe it is. And I'm just trying to get a basis here of who... Because if this doesn't work, if we don't see like major changes in this, it means something inside the Monte Carlo filtering is we're not using predict correctly in that case. If the game actually finishes, we know that we don't use predict anymore. And the game actually finishes, we stop predicting. And that happens after 40 to 60 moves. So it's quite possible that after, yeah, even after the first 20 iterations, maybe one of them just takes control and wins the most. But no, then predict current wouldn't have had that much of an influence if that was the case. It really means that first prediction is good. Now, that's not an overwhelmingly negative score. We want an overwhelmingly negative. So let's go back to predict current and basically turn off the prediction. And this is pointing towards something more fundamental. We can do something even worse than predict opposite. We can do a predict loss. And that guarantees them all the same score. But really what it's pointing towards is that if predict opposite doesn't make a very big difference to predict state, it could indicate that our prediction is essentially random, because predict opposite on a random value is going to give you a random output as well. Why the hell is my fan so loud? It's spinning fast, and I'm not clear why. Something. Oh, now okay. Now because it's sorry. Now because it's actually using all those controls. Now it's because we're actually running the simulation at, you know, C635. It's using that many cores. Oh, I forgot to limit the cores, but that's okay. I guess the streaming's still working. All right. So here we have an overwhelmingly negative against predict current. I guess. Well, I'm deciding how much longer I spend on tic-tac-toe because I don't see a clear strategy going forward. All right, but we've confirmed, basically, we've confirmed one thing. Our score predictor's garbage. Now, how can we improve the score predictor? This is what really sucks, is that how can we improve the score predictor? Hypersonic, I don't get the reference. Oh, there's a cell. Or you're saying another game. We should just go to another game. Let's see where we go. Unless I can think of something genius to do with the predict. Wow, so that's the Bomberman game. I'm writing this down, hypersonic. Okay, so let's recount where we are. We're using Monte Carlo. We don't get good depth. So we introduced a scoring function. And we do that in the strategy. When we play to the end, we do play to end, play to end. It takes a predict now. And it has a maximum depth. And it basically says, if we reach that maximum depth, let's just predict who wins. And this was to increase the number of iterations. Now, IKFS, we're doing well for Rust learning. We have lots of different stuff in play now. But we're slowing down that. Like we have the closures here. We're boxing stuff up. We're using this fun thing here is this par-iter. Par-iter coming from the, which library is that? From Rayon. This is how we got the 8 threads in parallel to do an iteration. So our iteration of 8,000, this spreads across my 8 threads. And this was part of the Rayon's package for Rust. So we've done some Rust threading, and we sum it up here. And so we actually do the simulation in parallel, which gives us 8 times as fast. So we are doing that. We're slowly getting improvement on that. So the Rust learning is getting there. Boxing up strategies, how to cast closures to strategies. Lots of little things, not major steps. We have the test cases in this program as well. We've done benchmarking before. We haven't added it back, though. So there is Rust's learnings in here, just not so many yet. The next step is going to be the ref cell and RC on everything, and that's probably, if I go to Bomberman, I might do that, ref C and RC, because we need to have links around. Okay, so let's go back to break. So the strategy was that we wanted to increase it because the number of counts, the iteration depth on Monte Carlo, we couldn't get enough of them. We only got like 100 iterations. So we introduced this max steps. How deep do you go before you say, hey, look, it's too far. Let's just predict who's going to win based on the current board state. And it's supposed to be rough estimation. Technically, Monte Carlo is supposed to do that, but we said let's even cut it short. And so as we've just shown, our prediction algorithms are total garbage. Just not giving a prediction is better than what our prediction's actually doing. So let's go back to the first one. Let's do a prediction depth of 90. By saying playing out to 90, the game can have at most 81 steps. So 90 here says basically you never do any prediction, just play the game to the end. The number of iteration goes down a lot, and that's the problem. Let's see, let's check that state again. And we want to verify that this isn't failing on us. Because a depth of 90 against a predictor, if it's better, then we stick with there. And we look at another thing that instead of doing play to end, we do a different option. And we can definitely improve, I don't know if we definitely can, we may be able to improve the predictor using heuristics. Instead of doing the counting approach, we may just look at the positions on the board and decide who might win this board. I'm not totally confident in that. I mean, my confidence in the predictor has basically gone entirely now. Yeah, Bomberman, I guess Bomberman is another coding game thing. We can just run through all of them. If we don't like these, we can come back. Some of the guys there, like the guys we're competing with, obviously have a lot more AI experience than I do. And the advantage of just jumping between games, it's not like I'm giving up on this. The advantage is that we get to learn new things. Because if I get stuck on tic-tac-toe now and I don't know what to do, it's not helping anybody for me to sit here. Alright, you can see this clearly. Look at this one. Hey, wait a second. This value 10. Oh, I think I've been doing my calculations wrong. That's the number of milliseconds we have. How many do we have in the game? I thought we have... Tic-tac-toe, we have 100. I put it down to 10 because I was going in release mode, so let's do release mode instead. Compare those two. It'll take just as long, but we get more things. This is in here 10 milliseconds. That's a really low prediction. 10 times slower than what we're allowed. So I do it in release mode, we'll see, but obviously, yeah, we're trying to see, does a bigger depth actually help, or does prediction actually help? And so this is our baseline again. This one here says go to the end of the game, and this one here says go 20 depths and then use the predictor. And we want to see which one actually gets a better score. If simply going deeper gets a better score, then there's no point in doing prediction. And again, this timeout, this is a timeout here saying 10 milliseconds. Since we're in release mode here, we're cutting it down from 100. Obviously, better depth is higher, but it does fewer iterations. There's fewer iterations happening in that depth. It takes just as long to go in release mode as debug mode because of the 10 milliseconds. 10 milliseconds, 10 milliseconds. It's not gonna go faster. Yeah, now this one is slightly better. Player 0, a deep prediction is slightly better than one with the predictor. But this was the original idea why we thought, well, maybe prediction's good because it's not overwhelmingly better. Like, I really want to convince myself that this is actually working. Let's give it twice as long. That should increase its win rate significantly. IQS, do I simulate inputs blindly or take it in turns? I'm doing it in turns. So the stepping through the Monte Carlo is actually taking back and forth between the turns. And that's one of the cases I said possible improvement here would be instead of actually playing the game to the end, I just fill up the rest of the board squares with X's and O's, because that would be super fast. It wouldn't be valid, but it would be super fast. And then that would basically increase the number of iterations. Just flood the board and see how many X's and O's there are, because calculating state's a bit slower, but it's okay. We have to calculate state anyways. But right now I do just play it to the end. I just swap randomly, I play down. So I take the first move and I randomly play down with Monte Carlo based on all the positions you have. Just randomly pick a path to the end of the game and then see who wins and do that, like, I'd like to say thousands upon thousands of times, but as it turns out, hundreds of times, which is just not enough to do a comparison. That's why we got this prediction mess of trying to figure out, well, can we predict something else? Can the predictor help us get the depth down? There's absolutely no value of improvement here. And this is one of the cases I mentioned on Twitter. I brought it up and I said, my impression is that Rust is slow in this regards, and I couldn't give concrete examples, and it's fair to ask for them, but this is the case here, is that even in release mode, our get state function seems way slower than it should. Okay, so but we actually verifies that giving it more time definitely works. Clearly. This is an overwhelming win. But even this is disturbing, right? Because we're playing 1,000 games. And it's still not winning all of them. So our algorithm, even at that depth, it's just not good enough for Monte Carlo to make a decision. So let's increase, let's just let this run for a long time as we think about this, is that this points to a serious problem that during the initial game, we can't be using Monte Carlo because it's just not deep enough. And it looks like, and because of that, it looks like some point in the game, like 20 moves in, it looks like the winner of the game is highly decided. Because otherwise the Monte Carlo predictor would actually always win. That is, if there was at phase 30 of the game, if Monte Carlo, if you still have a chance of winning, this one should improve that. But those results are basically saying, at this point in the game, It looks like the decision's already been decided, which means there must be a predict function which gives which could be written. It points towards us being able to write a predict and scoring function, but we don't know how. And so that'll be the key. How can we write a prediction function? Can we just look at a board and decide who's going to win it? Other than the few cases where it's trivial, I'm not sure we can. And that was where I was splitting this off, is that if this doesn't work, we can either move on to another game, or we can move on to learning something new, and that would be a multi-level neural network. Because I strongly believe that given the state of the board, given the appearance of a whole board, I strongly believe there's a way to predict who's going to win just based on that input. If there is, then we should be able to train a neural network to tell us that. The neural network then is going to be super slow, super fast, because it takes 81 inputs through 3 layers, even 3 or 4 layers of neurons. Is going to be extremely fast compared to any sort of iteration. And if we do think this is possible, and we can train it, and we can create a high-value scoring function, that will make a huge difference in how our games come out. The question is, can we actually do that? Given the state of the board, can a neural network predict who's going to win? Or who has the upper hand? It's basically who has the advantage. At this given point, if you played perfectly, who would have the upper hand in winning, player 1 or player 0? If a neural network can actually predict that, then we can write a perfect predict function. And with a perfect predict function, Monte Carlo gets a lot better. And you have a lot better options. You could actually, if you had it perfect, and if it had like a really good perfect, then you could actually reduce the Monte Carlo to even not going as far down. Alright, so every time we increase the count. Alright, but this one here, and this is... So player 1, he won a lot more. Now remember, this is wins minus losses, so 500. He's probably won about 750 of them. Right, this is the score. I wonder if I just put 0 so it's clearer. No, just leave it. That's fine. So he's won most of them, but the thing is here is that he hasn't won all of them, meaning that randomness is still winning. Randomness is still becoming a huge part of this game, which is not what we want. It means our Monte Carlo is simply not getting enough iterations, even at this high count. It's simply not doing enough iterations to be a useful strategy, unless predict can be improved. How can we improve predict? So again, predicts. The options we have predict is predict current says just the current state. If it's open or closed, it basically doesn't rank the value of the game. It's just going to say, I don't know, it's fine. There's no value to it. And strategy, where do we do predict? We do predict state and play to end. Let's look at play to end. What does play to end do? Now the one thing we could try and play to end is that winning is clearly 1 and losing is clearly -1. It's hard to say whether a closed board is worth more than an open board. Because I'm treating both ties the same. Ties are not good outcomes. I don't think it'll make a big difference. I can't. We could chart it. So what do I... Now we don't do sorting on the Monte Carlo predict because we just don't have enough inputs. But let's actually add it back in. And this focuses our goals on the winning ones. This is the true Monte Carlo now, the sorting, and you increase the number of walks through the paths where it's actually winning. IKFS, I don't entirely understand what you mean, but I can explain to you. What I'm doing in predict. Again, we're not using, right now in the actual playing, we're not using any heuristics, only in the prediction. And the prediction, the way I predict the winning of the big board is for each of the small boards, I predict the winner in the small board, which if it already has a winner, it takes that winner. So the prediction state, what it basically says, for a small board, we take the current state. If it has a winner or loser or it's closed, we return that state. Then we go into the silly logic of counting the ones and zeros versus to see who's likely to win. And the predicting of the state in the big board, what we do is we predict the state in all the small boards and fill in a new board, and then we get the result of that board. So it comes down to prediction of the state of the small boards, basically, who wins each one, that decides who wins the big board. But it's not just like then the small one, all we do to predict who wins, like tic-tac-toe boards, and it's really bad, I know, is we count the ones, we count the X's and count the O's. If there's more O's and X's, then it wins, otherwise the other one wins, and if they're tied, then the game is matched. Okay, so this, what I changed here doesn't work, and that was the this is the evaluation, the ordering in Monte Carlo. So I'm going to get back out of that. Yeah, whatever. So the easiest point we have to change right now, if it does anything, is in this predict small state. Can we predict, based on the game, is that can you predict from a small tic-tac-toe board who's going to win the game? Yeah, that's IKFS. That's what I'm thinking right now. Is should we choose to predict instead of just counting? Should we actually look at the individual states and decide? And I'm trying to avoid making this manual setup. This is why I mentioned the neural network. Is that if there is a way to predict a score, I'm pretty sure a neural network would find it, but we have to design it correctly. But is there a good enough way that we look for? Yeah, should we be looking here for ones that are partially filled and partially not filled? How can I do this? We could also do a mini Monte Carlo here, is on the small state. Just run a bunch of iterations and fill in all that ones. But I don't think that'll work. That just slows us down again. We need to be super fast. Now there are a bunch of board states where we know one player wins. If there's any possibility for like the player, if the player has two ends open, then they've won. But how often does it actually come up, and how can we quickly encode that into the game to figure that out without being too slow? How can I do that without counting? And again, this predicting small state is actually not fair because it's assuming that the ones and zeros are equally distributed, but they don't have to be because of the mechanics of the whole game. Because when you play in the big board, when you play here, the next player has to play here, is that the X's and zeros don't actually have to be balanced between the boards, although it often looks like they are. Okay, LKFS, we could try that. So basically you're saying we count every partial line. How many are there on a tic-tac-toe board? 1, 2, 3, 4, 5, 6. 2 per line. 12. There's 14. There's 14 twos. So we can run through each of those and count those that way. Well, let's try it. Let's try that. And we're actually going to compare it. So we're going to go back down to this 20 and 20. And we'll predict current. And the other one we're going to do is going to do predict state. So we only need to compare against current, predict state. And we can actually go down to, yeah, no, 20 is fine. That's, yeah. So get rid of this. And I had in state similar code to eval player. And we're going to do an eval player thing. Something like this. Let mut score player 0 equals 0. Let mut score. Well, actually, we can just have one score. Score equals 0, I32. Because we'll just do plus and minus on this then. So we have the two players, that's fine. And self the player 0, player 1. So we're going to do score plus equals if player 0 and wins equals win, then we do a both players can't possibly win, so we do a plus 1. Else, if the second player wins, then we do a minus 1, else we return it 0. So this does the counting here. And I usually get this wrong. It usually pisses me off. I can't do it this way. So eval player 1, we're looking for partial wins now, right? So let's just do a couple of these and see if it's compiling. And for partial wins, what I mean is that if we have these two filled or these two on the board, these are rows in the board. Let's just see if it actually gets this correct now. Cargo check. I don't know why it's compiling everything. I have no idea why check suddenly compiled everything. And this is actually state.board 0. Let's copy this bit out here. If score is greater than 0, then player 0 wins. If score is less than 1, then player 1 is 1. Otherwise, the game result is closed. We've only checked 2 states, though. Okay, so that's going to compile. So now we're going to go through all these states and keep adding them. And I'm going to make these all 0, 0 until we get them all done. We just have to know what all the winning states are now. Let's put a whole bunch of these here. Hard code these because, hey, that's fun. So 2 in a row, 2 in a row, 2 in a row, 2 in a row. Okay, 2 in a row, 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 2 in a row. In the middle, in the middle, in the middle the other way, in the middle the other way. Okay, so these are all the 2s. Now this is the part I was saying is that I'm not impressed with Rust's speed here. this algorithm here, this get state, when we compile this to release mode, this is taking like 130 nanoseconds, which is ridiculous for a bunch of OR operations. This really should come down to like 30-40 nanoseconds, and I'm not sure why it's so slow. I mean, it's probably not the critical point in our code. It's not going to help us a lot, but this is one of the points is the code is looking at was way slower than I thought it would be, and I'm guessing it has to do with these lookups here, and I don't know how to get rid of them because it's doing checks on them. Alright, so predict. So we have that improved predictor. Well, we're going to find out if it's improved. Variable build-release and build/play. No, target/release play. So we have one that predicts state, and this is our new predictor, and one that predicts current. If the predictor is going to help, player 0 should win more often than player 1. If predictor's not of help, then it won't. If there's an error in the predictor, we don't know. Are you sure there's 24 rows? I thought I calculated, how many do I have? 21, 2... So I have 15 of them. I just did this in my head. There's... Oh, I know which ones I skipped. Yeah, I can. That's exactly. I got the exact thing right now. Yeah, those are the ones I skipped right now. And so let's group these in groups of 2. These are the vertical ones. And Tom, we can check that one too. Okay, so this adds the 6 more, I think, that we need. 6, 6, 18, and 22. What if we missed? I have 22 now. Ah, yeah, the verticals, the horizontals as well. There's 2 more here for the 1, 1, and 1, 1. Those are the 2. That's 24 of them. Let's hope that's the reason player 0 was doing so bad. Oh, wait! I have an error in this. Ah, crap. There's an error in this. I'm checking the individual players. So I'm actually not checking for an empty space there. I'm just checking to see if they actually have those positions. It doesn't mean there could be somebody in the middle of it. We actually have to exclude player 1 from this as well. Shit, this makes it slower. Makes it harder to do. Alright, he's losing horribly. He's making a... Well, we know... Well, we verified that making a bad prediction... Okay, but what I'm saying is that we have the right now is that it's hard to show on this board. So if I have XX, these 2, like say this board up here, these 2 X's, our current score is counting this as a win. Because it has these 2 X's. Wonderful. It's not checking the fact that the 0 is there. So we actually have to check for the open ones as well. It's starting to get slow. I'm just going to open this up for reference here. What's a quick way to check this, though? We have to have a second bit mask here saying which one's open. Yuck, 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 yuck. Open expression. Well, this becomes suddenly a pain in the ass. Oops. Now this looks like a lot of code, but in theory this should compile down really fast, as we said. It's just a bitch of binary operations. I mean, there's still a lot of them, though. So this one here, we're assuming this one is free. This one's free. This one's free. This one's free. This one's free. So I'm just marking the ones that have to be free still. This one has to be free. This one has to be free. This one free. This one free. This one free. This one free. This one. 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 Okay. So we have this. If we need a board though, oh come on, we need the board as well. If P0 or P1 and open. It's not equal 0. Then we can do this. This is now a lot of branching, so the CPU could actually be slow in this because they have tons and tons of branching here. There's ways to avoid the branching. We hope there's a bunch of ternary operators involved, but still, this is going to be slow. So what I'm basically saying is only if that spot's open, only if the open spot's open, because P0, P1 says the complete combined version of the board, and open, if it's something other than 0, it means that spot's filled. Okay, good. Now, as you start worrying about the cost of this, prediction might start getting slower. Again, it's just a whole bunch of binary operations. There is branching in here, and there should be a way to do this. If this was really good, there are ways to do this without the branching, but well, it's still going to be branching. There's just operators that might make it better. Ho hum, ho hum. Oh wow, it's done even worse now. That's scary. This can't be right. Okay, IKFS, the issue with performance and the reason why performance is important is because I can't really test without performance, because I have this predict state and it's allowed to take 10 milliseconds to make its turn. So if that function takes really long, every time that function takes longer, it means it evaluates less and less things in the Monte Carlo. Right? And so performance is an issue because I have that fixed thing saying this is how long it takes. Now the other option is I could base this on instead saying, well, how many iterations can you do? But we know for sure the Monte Carlo is that if you give it more iterations, it does better. And so it has to be this balance. So the way performance is an issue. And now I wonder, is this really reduced score here? It's just because it's really slow? Okay, I guess it's not that Monte Carlo producing crap. The Monte Carlo produces good results. It just doesn't run enough iterations. We're trying to find a way so it can run lower iterations and produce better results. That is, if I let Monte Carlo do 1,000,000 iterations, it wins. That's why I increase the value here. This value here is how long is the Monte Carlo allowed to run for. And if you let the Monte Carlo run faster, it improves its results. And if you let it run to the end, it improves it a lot. Like if you say let it run to the end and it gets 1 second per move, it's going to win. It's definitely just, it doesn't make any predictions, and it just runs millions of iterations. This one's probably actually 1,000,000 now, and it will have some phenomenal win rate. But what we're forced to deal with now is basically, well, we don't have that much time. We only have 10 milliseconds, and if we let it evaluate to the end, there's not enough of them, so we say let's cut it off, and now we have to guess the state. And the state predictor here says, well, this one's making it worse. And the thing is it making it worse because it's actually worse or because it takes lots and lots of time? So let's time this function, roughly. We have this perf thing here, perf. Where's our perf stuff? So let's do another perf test on that to see how long it's actually taking. We're just going to time one of them in a very bad sort of way. And what do we want to do? Let result equal predict, and we have to open that up. We'll just do predict state, the whole predict state. Predict state, we need a board somewhere. Where's our board? Board state. Let's take a default board state. Print line, we're going to say predict state has some sort of result here, this long, and you have to print the result just to make sure it's used. The actual benchmarking thing has little black box things to do that. We're going to assume it's still in subsecond or nanoseconds. And let's see how long that performance takes. Okay. Oh, perf doesn't have that anymore, so let's just run perf that way. And get rid of all the other ones here. Don't need this either. Board state. Why does it not have board state? Can't create a board state. Default, the default board state. Now this will affect the results by using a default one, but at least we get a limit of an idea of how long that function takes. Using one iteration, which is not wise, but we're hoping it comes back with a trivially small number. If it comes back with any significantly sized number, then it's an issue. Okay, so this number's fine. Alright, so this is... I mean, this number's not fine. I mean, this number's awful, to be honest. 1.3 microseconds. Yeah, that's bad. This function is taking 1.3 microseconds. Let's run it again. Target, release, play. Alright, and this is what I mean about performance in Rust. Why is this taking 1.3 microseconds? Tom, I honestly don't believe it's these values here. Watch. Let's just do 0U16. Let's eliminate these first of all. You know what? I have this checked backwards. This has to be equal 0, but it won't change the speed. And let's try that again. So we got that backwards. I might explain why it's slower, but let's see. Wow. Okay, so the state board here is definitely slow, so we can definitely change that. Get unchecked. Let's try it. Yeah. Relax. What the hell? What the hell? Why does that increase the time? That's just the first time. Because I'm calling debug, that's why. I'm running the wrong one. Release. I can't because I have multiple programs in here. And we tried to get the syntax working right, and it seems to keep getting mad about which one to run. So I just build and run that one then. Alright, so this actually doesn't speed it up at all. But the speed of this function is problemsome. And I mean, you shouldn't measure speed based on one iteration, but when you have numbers this big, you can be reasonably assured the speed sucks. So, well, I don't know what the name of the program is. It's not a crate name. I don't know what I'm trying to. I want to play. Bin play. Oh, it finds it. Okay, that works then. That'll save me some effort. Okay, now let's go back to play and figure out. Knowing that that takes so long, let's verify this first. Let's give it twice as much time for the predict state. Again, this biases it now because that's more iterations, and we should actually put a fixed iteration count to find out, but this should more than compensate for that 2 microseconds that function costs us. So an awful function. If it doesn't compensate for it, it means the predict state is probably not any good. Again, that's not the one function. That has to do that 9 times for the whole board, kind of. So it's not. But if we can improve the speed of those, it improves the Monte Carlo as well. But I'm just not seeing a clear way in how else to get the state of the board, to get the state of the win. Again, this compensation here by giving twice as much time should more than make up for that slow function. And we're expecting player 0 to win by a significant amount. Otherwise, it means predict state is not either not working, which is possible, or is not helping. And I don't have much more time today, so let's see what the results of this are and get some ideas. And if I've made no progress and I have nothing to predict state, we have no idea, then I think I might switch games just because I don't have an idea here other than doing the neural network. But if this doesn't give us a good result, yeah, it's not enough. It makes me worry that there is no way to predict the state of the game. This was... because we don't know if it's slightly better just because of the iterations of the Monte Carlo. But let's put it back to 50. We said we had 50 before. And this should be, if predict state is working, this should now really be an overwhelming win. If not, either this predict state approach doesn't work, or there is no predict state that actually works. And I still have no idea what the other people are doing then. Like, let's check the game again. Let's check the leaderboard. And again, it's disconcerting that the top players here, C++, C++, these are optimized probably, but not. They still don't have optimization mode. We know C++ can force it on. But again, it doesn't take that much to get values up this high. You only have to win a slightly more chance. The Java one, yeah, but this can be optimized fairly well. I think their VM's probably optimizing on the fly. You don't see a lot of other languages down there, C#. But this is the one here, the PHP one from edA-qa, which strongly indicates that there's something that doesn't require millions of iterations unless the PHP compiler has a way to significantly improve since I've last seen it, which has been a long time. And there just means a different way to go, and I just don't know what that way is. We had to find a new approach. It's like, I wish you could download one of them, like download the top guy with like his score and compile it locally and see if a longer run of Monte Carlo would actually beat him. It's hard to say. I mean, and so the fractal AI will be useless here unless we can find a predict algorithm that works. The fractal version of the Monte Carlo is utterly useless because it requires that scoring different. It requires a differential scoring, and the only other approach I can think of, unless somebody has an idea, is if we don't have this approach, is again just to use a neural network to program the predictor, but I'm not so keen on that because we don't have strong evidence that it works. We only have strong evidence that makes it worse. Which again, evidence that it makes it worse tends to be evidence that it could be better, right? Like if putting a predictor always makes me do the wrong move, then in theory you can just do the opposite of it and do a better move. But yeah, that's so far increasing this number. If I recall back up to 50, it gave it like a 500 win rate. And if the predictor is working, it should give us even higher win rates. But again, less things, so we're going to see what happens. And probably done for today because I only had a little bit of time to look at it today. We're going to see what happens. And then I think I'll move on because unless I have a sudden idea that I can try offline for how to play tic-tac-toe better, some sort of heuristic, but I don't want to go through heuristics. And okay, it has a win rate, but the predictor's not doing a good job. It's just the Monte Carlo, it's just the iterations that made it go better. Because it looks like iteration, so it's just winning. So our predictor is useless. Our predictor does nothing. And which either means you can't predict the state, which is possible, to be honest. It's possible that given the current state of tic-tac-toe board, you can't create a one-pass function like a linear combination of the inputs to say who's most likely to win. I mean, near the end of the game you can, but near the end of the game we don't need that. It's near the beginning of the game. Like when you have just a few, like in this state here, can you actually predict who's winning from this state? If you can't, then our approach is invalid. If you can, then great. So I don't know how to improve this now. I'm stuck. I'm stuck with it. Obviously performance would help if I can just run it more, but we can't. And debug mode, so I don't know. The approach we have requires a predict function, and I don't know how to write a predict function. I don't want to go into the neural net aspect of it because I have this weird feeling that it won't be able to figure one out either. Again, to train, and if we need to train a neural network, we have that because we have very strong evidence that if you just let the Monte Carlo thing do its thing, like run a couple million of iterations, it can predict who will win. It has a good chance to predict who will win. And you can use that to train a neural network if we had one. And I mean, speed's going to be an issue because a Monte Carlo thing that searches millions is going to take, it could be a minute per game or at least 10 seconds per game. But if there is a way to train it, that would find it and that would be good enough. But I'm not convinced of that now. And that means basically, I don't know. I don't know how to proceed right now. And I don't want to just try random heuristics because we did that in the competition and it gets to a certain point, but this is the one really that heuristics are probably not your friend here. In the first two levels, yeah, our Monte Carlo did well up to Gold League because it was relatively easy to get by. And for right now, how we get it higher, I don't know if we use heuristics or whatever. We tried another strategy, so we tried another strategy that just always ignored the big board and played to win on the small boards. And we knew we could win the small boards. That didn't actually help. Just winning taking the best move on each individual small board was not a strategy that let us win, which was very curious. And we actually tested that one, so each small board. And yeah. So, I don't know. I think I'm going to give up for now. I'm going to move on to another game. We're going to keep our gold level rating. And if we ever have any great ideas for tic-tac-toe, or if they ever able in release mode, we can see if release mode actually works better on the server. But all the other ones will also have release mode. We have to keep it in mind. IKFS, if you draw, you count up the winners of the small boards. And the person with the more wins in the small boards wins. And if you both have the same number, then, well, it's actually not possible. Or is it? Yeah, because you can tie the small boards. If you don't, but basically, if you tie, you just count up the winners of the small boards, and that makes it. That does actually make a significant difference in the strategy. And it's one of the reasons why I just took Monte Carlo, is because there's too many interactions here to actually decide who wins or who loses. So we don't have a good predictor. I'm just going to leave this, and next time, whenever I do next time, I'm just trying to think of. Maybe we move on to Bomberman, or maybe I learn, or maybe we forcibly find one that actually, and if we, okay, if you draw on a small board, it just basically puts a dead spot in the big board. It doesn't count to either player, and it's just a dead spot. You just can't play there anymore, and nobody can win it anymore, and it's dead. Yeah, Tomcast, this I said, we actually have that strategy. We had a strategy called, I mean, not heuristics, but we did the small board one. So we had strat local, and we have this thing called get. We had to get best small move. And get best small move actually played each game to the end. I mean, we sampled it. We sampled it with a scoring to the end, but because it was a small board, we could do thousands of them. We're fairly certain the scored small board actually won, and then Strat Local basically just did that every time. For every board we're on, just try to win that one. Ignore the whole overall game, just try to win that one, and it performed poorly. I can show you that one once again right now if you want to see that. Let P0 be Strat Factory. Player box. New Strat Local. New player. Watch this win now. There's probably some combination here that actually works, like a strat local on the big board to say where you should play, but then it's hard to know if you'll win that one. So there are definitely some options here. I was hoping we could just do Monte Carlo all the way here. IKFS, I have no idea where you'd rank if you chose one that focused on drawing. But I imagine you're going to have the exact same problem because you have to be able to score that. Although on the small boards, it's much easier. Okay, oh wow. Our strat local player fails all the time now. So our Monte Carlo one kicks its ass. That's the strongest difference we've seen the whole time, is a Monte Carlo one kicking its ass. I don't know how long it would take me to like when it bases it on tying, just going for tying. But that is one heuristic-based approach. It's basically, and I don't feel like doing this one right now, but it's an approach that if you take the big board, consider the big board, and take Tom's approach or take our approach or stat local. Basically, choose which spot you want on the big board, and which spot you don't want the other player to have, and always play there. And if you're playing on a spot you don't want in the big board, then take IKF's approach and say, well, just take the small board and put that one into a place where it ties. Like focus on a tie there. Play the best move to get it to tie there. And always focus on the big board. That is something you could try, and that would take me probably a couple hours to write up right now. And if this week I decide to do it, I'd probably do that offline and I can test it, or it'll be an early session during the day and I can let you know. But that is an option to try, and there's no indication whether I win or not. It's just some random thing. And again, we can compare it against the Monte Carlo one. We definitely have that option, but for now I think I'm going to leave it in next game. I mean, we're still in gold. We got to gold extremely fast, and it wasn't that hard, but and I don't want to just keep trying heuristics like that. We did that in the competition, and I think they work well there in like the competition mode, like the superhero one we had, because everybody's kind of in the same thing. They're trying a whole bunch of random things. Nobody's actually trying to create a really super powered thinking ahead bot, or maybe they were. I mean, the top guys could have done that. And I wanted in this one to actually think of the theoretically correct one. And the Monte Carlo would work, but the time constraints just destroy it. And the suggestion of the fractal AI doesn't work because you need a scoring. If you can't score it, it's useless. And I don't know what other approach is. The only, like I say, the only thing I know, other than resorting to like manually programmed heuristics, are let's create a neural network for the predict function. And this assumes there is one that works. If there is one that works, we'll find it. Otherwise, we might just prove there isn't one, in which case then we're stuck at the same place of not knowing what to do. And yeah, IKFS, yeah, that's where our timeouts come from. Basically, we kept putting we limited the search depth, and we have this trade-off. As we limit the Monte Carlo search depth, we rely more on the predictor. And we basically got the point is that as we reduce the search depth, we know which works and what doesn't work, but we're not improving our rank, we're just maintaining it. So we have to find out something else. And the one we submitted now is the Monte Carlo one, and we're just going to leave it at that for now, I think. Okay, so that's all the time I have for today. Then hopefully this week I'll do a few shows, but I will be doing the Leaf compiler a few times this week. I said I do have some like actual OpenGL stuff in Leaf. I have some stuff working. I have the basic arrow keys working on the keyboard to move the Leaf around the screen. That would actually be enough to start doing the Tron-based thing. So maybe I'll do that, and I can start explaining. The idea behind the Leaf stuff is I'm actually going to start explaining the code I do here visually, because you can't see it here. I'll start explaining how this code works, like the trees, like the filling and stuff. And I thank you for joining me today, and we should see each other again this week. Thank you very much.